I didn't think about, I don't know, I don't have any, I'm so sorry. Yes, I guess I'll just hold it in my hand. I think that should be okay, right? Or
Yeah, it's fine. I'm just trying to think if there's a better solution for you.
I don't think it, unless you think there's going to be
Unless
some.
someone has, like, a belt or something.
I have a belt, but it might look kind of funny.
I have a sweat. Oh, wait, sorry. I can hang it like in my back, right? Here, maybe. Can you please like help? Do you think you can help?
Do you want some help, like, clipping it on?
Yes, just clip it on to that thing.
Okay, I don't want to get your hair.
No, it's okay.
I hope this isn't too uncomfortable.
No, I mean, as long as it stays.
Okay, I think that's good.
I hope so. Okay.
It's a whole new thing.
I'm sorry. Yes, I didn't. I just didn't think about it.
Hey guys.
Yeah, please go ahead.
So for everyone here right now, just real quick, student talks start today. Check the schedule that was sent on the Discord, I think, for day 1, Wednesday. We can go down the top of the list. People can volunteer to go first, whatever. But the plan is basically right after the second lecture for like 30 minutes, we'll have 6 people go. And then we'll go to lunch. And then right after the 4th lecture, just before dinner, we'll have the other 6 people go. So neither meal gets too cut off. And we'll do it in this room. So just stay put after the second lecture. If you're on the list, be ready to just come up and speak. If you haven't made slides yet and you signed up to do slides, we actually prefer chalk talks because it's just going to be easier than using the projector. So if possible, we prefer chalk. But if you really want to use a slide, try and just like maybe like one slide, more like a poster than actual slides because it's only 5 minutes. Any questions about the student talks? Also, I think at some point, what was originally day 2 and day 4 got swapped. So make sure to double check that you know what day you are, just in case. Just double check, yeah. Any questions? All right, thank you so much.
All right, and we will remember do our TASI photo right after this during the break. So we'll turn it over to Anna for her next lecture.
Okay. Good morning, everyone. Thanks for coming. So let's briefly recap where we left off yesterday. So we talked about basically this notion of conformal spacetime primaries. And we used that to define certain quantities constructed from metric components that transform in representation. So that notion of conformal primary was equivalent to saying that we want to construct some bulk quantities. I wouldn't say fields because we saw that they are nonlinear in the metric components that live in these representations, basically. And once we've done that, we are able to identify some covariant quantities, QS, for S equal to 0, 1, and 2, that replaced the Bondi mass aspect, angular momentum aspect, and this TAB function that we saw when we discussed the general asymptotically flat solution to Einstein equations. Okay, and then upon doing that, what I claimed, so I haven't proven for you, but I claimed, so that this is true, that the constraint equations at scribe, so the GUU, the UU component, the U, Z, and Z bar components of Einstein's equations, together with the GZZ and GZ bar, Z bar ones, half of those will become basically these equations. Equations that are recursion relations that determine the S equal to 2, for example, quantity Q in terms of the S equal to 1 and S equal to 0, 1. So remember that S equal to 0 was roughly speaking related to the mass aspect. This one, the S equal to 1, was related to angular momentum aspect. And this one was related to something that we haven't really to something new, but it's a subleading component in the transverse component of the metric. Okay, so so here we have these equations that I talked about. There's six of them. Here we only have 3. But remember that these Q's were actually certain versions of these quantities projected onto the positive helicity component of the null frame that we talked about yesterday. So there are another 3 equations for the barred versions of these quantities, roughly speaking, for the opposite helicity ones. So there are 6 in total. So these are just a repackaging of the of the Einstein constraints. So okay, and I also said so we said yesterday that Q minus 1, one can identify it to be a half dn, and Q minus 2 is a du of n, a half du of n. So n was the News function, the negative velocity of the News tensor. Okay, so if you remember the discussion in the first lecture, we talked about constraints in that case. So we want to impose, so physical states should be subject to these constraints. So how do we impose these in the semi-classical upon quantization? So how do we quantize and how do we impose these as constraints on asymptotic states? So, yes. That is a great question, and that will be the punchline for today. We will discuss that later, but let's first understand these ones. Okay, so I'm going to keep this in mind because we're going to use it. Okay, so what do I mean? How would we find the action of these guys on the asymptotic, on asymptotic states? Well, first of all, one should identify the phase space. So that's quite it's a broad subject, and there have been many developments there over the past years. So I'm just gonna kind of very briefly sketch how one would go about identifying the phase space of theories of gravity in asymptotically flat spacetimes, or more generally, theories of gravity. So I'm going to swipe a lot of subtleties under the rug, and I'm just going to do the most simple example to just illustrate sort of like how this phase space should look like. So what should it be parametrized by? We should be able to identify some pair of canonically conjugate variables, basically, or pairs thereof. So usually, we start off with the Einstein-Hilbert action. And you may remember that if we consider a variation, this is a standard thing in classical field theory. If we consider a variation of the Einstein-Hilbert action, we expect to get something that is the integral of the equations of motion. So sorry, here I'm varying the Einstein-Hilbert action with respect to the metric G. And then, but in general, in order to put this into this form, you will have to do some integration by parts. And usually there is boundary terms that you're going to pick up. So I'm going to call these theta g of delta g, which is some integral over the boundary of some quantity that one can determine very explicitly. The idea is that this was shown in papers by Wald and collaborators in the early 90s. One can use sort of this term to be able to identify a symplectic structure on in gravity on a particular that would live on particular Cauchy on any Cauchy slice. So this allows. Sorry, I should say that this delta means variation in field space. So it's the exterior derivative in field space. And so this object turns out to be a one form in field space. Now I can take another variation of this object to obtain a two form in field space. And that two form turns out to be a symplectic form on the phase space. So the phase space turns out to be a symplectic manifold, and there is an associated symplectic form that one can construct by computing the exterior derivative of this theta term, which is called the presymplectic potential. So And so for a nice review about this and subtleties in this business, you can check out some lecture notes by Compare and Fiorucci. So 1801-07064. Yes.
Usually these things are defined by integrating over a Cauchy slice.
Yeah.
Here we'll again make that connection of Cauchy slice with the boundary.
Yeah, so here my M is asymptotically flat spacetime. And the boundary here is essentially, so there are subtleties with space like infinity. One has to resolve that. But the boundary consists of this collection of null cones, as well as the resolution of I naught and potentially the resolution of I plus and I minus. So I don't really want to go into all of this. Here I'm just evaluating the contributions from scry plus and scry minus, because you would expect those to be the only things that would matter when you only have pure gravity, so massless particles. But there is a huge literature of all sorts of things related to your question. Okay, but the point is that just for the pure gravity case that we discussed before, one can evaluate this very explicitly. So you can just take the solution, this ansatz that we discussed yesterday, and plug it into the formula for this and compute this variation. It's just a calculation. And you find, so for the asymptotically flat metric discussed before, so just pure gravity. We find, and I'm only going to look at the contribution from scry plus, but there is going to be a similar contribution from scry minus. We find scry plus AFS is 1 over 16 pi g Newton, and then we have some integral over scry plus, and then we have CZZ wedge and z bar plus the complex conjugate, Hermitian conjugate. Oh, sorry, there is no wedge here. Sorry, it's just O. Okay, so this is one form in phase space. So this, yeah, we also call this C, and we also call this N yesterday, and this is C bar, and this is N bar. So this means that the symplectic form omega is just obtained by taking another, sorry, I missed an important term. And here you're also going to find some terms. Actually, you're going to find a lot of terms that are actually phase space exact. Not going to write them down because we're only going to care about the symplectic form, which is not going to see these terms because the delta squared is equal to 0. So delta is exterior derivative in phase space, so delta squared is 0. So we get that omega is 1 over 16 pi g Newton. And then we have integral over scry plus of delta C wedge delta N plus delta C bar wedge delta N bar. So from here, so all of these quantities are functions of u, z, and z bar, okay? So from here, we can read off the symplectic form and hence the Poisson bracket, just like you would in classical mechanics. Yes?
Yeah, very simple, maybe simple question from like what you have over there. It seems to be delta c times n bar plus delta c bar times n. And then here, like after you take another interior derivative.
No, you are totally right, except for I defined n in a funny way. So my n was defined. I'm very sorry about that. It's I apologize on behalf of also my collaborators. We just thought that it's more nice to see that c is canonically conjugate to n rather than n bar. Say that pairs of variables are c and n rather than c and n bar. So remember that I defined n as m bar a, m bar b, and ab, and c. So now sort of that justifies my conventions, but it's just a convention, and you're welcome to replace. Yeah, you're welcome to change it. But the point is that it's always the CZZ canonically paired with n z bar z bar. Okay. So this allows us to read off the symplectic. The components of the symplectic form, and those are related to the Poisson bracket, right? Yes?
Is one way to see why they're conjugate is that they're related by a du derivative, kind of like x?
Just intuitively in classical mechanics, if you just take a momentum, usually the momentum is, in quantum mechanics, momentum and position are the canonically conjugate variables, which you can obtain by similar analysis starting from a classical field theory, from a classical theory. And momenta and positions are usually related by a time derivative. So here, you can think about c as the position variable and n as the momentum variable. Yes? No, it is still even dimensional. Usually phase space is even dimensional. No, I mean the phase space is always the phase space is always even dimensional, but I don't think this, because here you have a full collection of fields, so I don't think that the phase space. No, I mean I don't think that's true, because you can take like a collection of, even for the harmonic, you don't need to have a space-time necessarily, right? So it shouldn't, the dimension of the phase space should have nothing to do with the dimension of the space-time. There is an infinite number of things here, right? Because c and n are actually functions of u, z, and z bar. Yes? Yes?
Usually, when we talk about pieces of data, but here, if I give you c as a function of u, then I automatically know n, right? Because it's just the u derivative?
No, but you run, similar confusions you may have in classical field theory. But one is supposed to think about the momentum as the derivative of the Lagrangian with respect to the q dot, with respect. I'm just saying that even in classical mechanics, momentum and position naively are related by time derivative. But when you think about them as variables on phase space, you should regard them as independent variables. So similarly here. Okay, so we can read off the following Poisson bracket. So n of u, z and z bar, bracket with c, u, z and z bar, is and I hope I may have gotten factors or signs wrong, so I'm just going to put proportionality sign. 16 pi g Newton, and then we have some delta 2 z prime and some delta u minus u prime. Okay, so the funny thing here is that the thing that maybe you should find surprising, maybe not, is that this bracket is non-vanishing. So let's contrast this to ADS-CFT. If I were to do the similar calculation in ADS and say evaluated the symplectic form on near the time-like boundary of ADS, like we did when we discussed this radial quantization idea and these Wheeler-DeWitt constraints in that case. So there you would find that the symplectic form, so you wouldn't find that. Actually, there is a symplectic structure, but roughly speaking, it pairs the degrees of freedom associated with the metric near the boundary and then sort of the conjugate of that would be some, roughly speaking, the stress tensor in the CFT. And usually we fix the metric on the boundary, which is equivalent to demanding that the symplectic form actually vanishes in that case. Here, that's manifestly not true. So if it may be true that if you evaluate the symplectic form in the resolution of I0, then you're going to find a vanishing answer. But if you evaluate it on scri plus or scri minus, that definitely won't be the case. And another way to say it is that here you may say, but OK, in ADS-CFT, we usually impose some boundary conditions. Why can you not do that in this case as well? So, but here the point is that there is only two things that I can do. I can either fix CZZ or fix N. Sorry, I can either fix C or I can fix N. But actually, in gravity, I'm actually not allowed to do either if I want to allow for the presence of gravitational waves. Because a non-trivial C, I need a non-trivial C to have, in particular, I need non-trivial N to have a gravitational wave, to allow for flux at infinity. Yes?
Perhaps you said it, but in this case, I am not yet supposed to have a metric that is asymptotically flat. Because also in ADS, what we impose is that like just the metric is asymptotically ADS.
But yesterday we wrote down an asymptotically flat metric.
Yeah, no, exactly. But like in ADS, that's like a boundary condition that we have asymptotically ADS.
Yesterday we imposed the boundary condition that we get asymptotically Minkowski.
So, okay, good. And so, why then I don't get the same thing? Like, what's the intuitive explanation?
Yeah, the intuitive explanation is that the gravitational fields actually fall off quite slowly in flat space, and you have like these 1 over r. Gravitational waves go as 1 over r in flat space, and you have these non-vanishing contributions. Yes. Thank you for the question. OK, so I hope the idea is clear, but okay, there is a whole story with like soft modes, edge modes, and other things that add extra structure to the phase space. But here I'm just going to focus on this very basic, most basic thing. And this was actually derived by Ashtekar a long time ago. So in the 80s. So yeah, the other stuff came later. So OK, so now, why do I want this? Well, because we are interested ultimately to see, we want to, well, in the plan yesterday, I said that I want to identify some charges and connect them to the soft theorems. So first of all, we need to understand how these quantities act on the phase space. So in principle, one can already use this to find the action of this constraint of star on asymptotic particle states, in particular asymptotic graviton states, which roughly speaking are just of this form. So where C is the Fourier transform, C of omega is the Fourier transform of C. So we discussed this in the first lecture a little bit. We're going to come back to this. But let's just wait. So later we're going to do this explicitly. Well, but before we do that, let's just go back to those equations and look back at those Qs. So yesterday we talked about how Q0 is related to the body mass aspect. And it's known that the body mass aspect is the generator of so-called supertranslations in asymptotically flat spacetimes. And in particular, one would expect, in particular, at least for the s equal to 0 guy there, one would expect to recover some charge that generates supertranslations by taking the limit as u goes to minus infinity of this quantity q s for s equal to 0. So for s equal to 0, would expect to get something like this supertranslation So I know that I have not told you what supertranslations are, but you're going to rediscover that. So here, I'm just, another way to say it is it makes sense to consider this limit. Another way to say it is that, okay, in gauge theories and gravity, we know that there are some global conserved quantities or large sort of global charges that are defined on codimension 2 surfaces in space-time. So naturally, the place where these charges should live in gravity, just like the electric charge in electromagnetism is defined as an integral of the electric field over the sphere at infinity, here you might expect that the integral of the body mass aspect over a sphere at infinity to also be some kind of conserved quantity, okay? So that's all we're doing. But here I'm proposing let's try to construct these quantities for all of these charges Qs for s equal to 0, 1, and 2. So this is why I'm taking this limit. I'm going to define this as little Qs. This is generically a function on the sphere. But unfortunately, what turns out to be the case is that for s greater or equal than 1, this limit actually diverges. So I'm not going to get a finite quantity. I'm in general going to get some divergent terms. So these are very confusing, and maybe they're still confusing. But let's just, since I don't really have time to discuss this very much in these lectures, let's just assume that we subtract them off. And there is a way to do this consistently. So there is a formula that allows you to subtract them off, and it's motivated by imposing some, roughly speaking, you can think about it as imposing some further boundary conditions. So yeah. Keeping only the finite part, what one can show is that for s equal to 0 and 1, these Qs, Z, and Z bar integrated against functions on the sphere with appropriate weights. Generate an algebra. This means that when you compute their Poisson brackets, you get something that is if I take, for example, Qs equal to 0 with s equal to 0, you're going to get a Qs equal to 0. If I take s equal to 0 with 1, I'm going to get Qs equal to 0. You can check this. It's like a closed. There is a closed structure. The Poisson this Poisson bracket forms. It's closed. The space of Qs 0 and 1 is closed spaced under the Poisson bracket. So. And this algebra turns out to coincide with the extended BMS for algebra. So this is something that was first found by Barney and Trossard in 2011. using kind of very different methods. They used covariant phase space methods to compute these brackets. And what they found, quite remarkably, is that, roughly speaking, the Poisson bracket between some charges that they actually defined and computed associated with two vector fields, psi1 and psi2, is Q of the commutator of psi1 and psi2. So, and here, these vector fields psi are basically the sum of supertranslations and superrotations. Roughly speaking, these supertranslation vector fields are, they generate translations that are angle dependent at null infinity. So they are functions on the sphere d by du plus other terms, subleading in R, and psi SR, sorry, at scri plus. At scri plus is YA d by dA plus some other terms. Sorry, where this YA is a function of Z and Z bar as well. And so yesterday we discussed Lorentz transformations, which we saw basically took this form. But here the point is that both the Lorentz transformations and the usual translations actually get enhanced to an infinite dimensional algebra. So they are parametrized, these vector fields are now parametrized by a function and a vector field on the sphere respectively. And here, in fact, there is an additional constraint that dz of yz bar is dz bar yz is equal to 0 for this to hold. So yeah, if you check out this paper, it's really tour de force computation to show that the structure exists. What was unknown since Bondi, Vanderburg, Metzner, and Sachs was that asymptotically flat spacetimes admit these enhanced symmetries that enhance translations. So these are called supertranslations. The new element in this paper was that they actually found that there are generalizations of Lorentz transformations as well that arise when one analyzes the asymptotic symmetries of asymptotically flat spacetimes. And these symmetries are actually associated, they're generated by charges Q that one can construct. And one can show that they form, so in this Barnich-Trossard, they also had some central extension term here, K, but it turns out that for the supertranslations and also for these particular superrotations, this other term is not here.
Sorry, where is this central extension coming from? This is like a Poisson bracket, right?
It's some co-cycle on the phase space, and they analyze, I mean, they compute it in their paper. And in general, it's going to depend. So all of these objects are defined in terms of quantities that appear in these metrics, and there is they develop a formalism to compute this. I mean, in some sense, I mean, Wald has already told us how to compute charges in gravity in the 90s, and that this work is an extension of that analyzes asymptotically flat spacetimes. Yes?
Could you say again, like, what's the relation between C and QS defined on the left side?
Yes, great. So the relation between the two is that, so here, so the Q, let's be very explicit. I can define a QF as the integral over the sphere of f z bar QS equal to 0. And I can define a QY as the integral over the sphere of y z bar QS equal to 1. So these are functions on the sphere. All of these are local quantities here. And this QF would just be directly related to the supertranslation charge, so integral of the Bondi mass aspect integrated against the function on the sphere, whereas this guy would correspond to a subset of superrotations where this y is actually it's just one of I mean, setting one of the components of these vector fields to 0. Okay? And it's a nice computation. So we're going to come back to this later. But here, I mean, the point is that we didn't have, somehow quite remarkably, if you just study the constraints in this covariant way, in terms of these covariantly constructed quantities, one lands on this EBMS algebra quite directly, just using this Ashtekar bracket, because the QS 0, 1, and 2 are functionals of C and N, and one can explicitly compute their brackets to recover these results. Yes?
Is there a physical interpretation of these charges? Like for translation, we have linear motion at this point?
Yeah. Yes. These things generate, I mean, at this point, they just generate they generate, for F, so here if I chose F to be a constant, I would generate just translations in the U direction. And here if I chose Y's to be 1, Z, and Z squared, they would generate Lorentz transformations. Yes, we'll come back to that. Yes, they will be related to soft theorems. So at first, BMS, when they discovered them, they thought that there was no meaning, for example, to the supertranslations, but it turns out that there is a meaning. So yeah, actually, that's the next point. So why are we doing this? So let's now go back to these actions of this. So now, I mean, the point is that we have recovered these charges. So one can now study the effect of these charges of this. So these charges should give some conservation law. Okay. Usually, when you have symmetries and symmetries, Noether's theorem tells us that there have to be some conserved quantities. So how do we exploit that? So what are the conserved quantities, and how do we exploit those? So Strominger, in 2013, showed that certain so an important thing here is that we only talked about Scri plus. So let me write it here. There is actually a similar analysis at Scri minus, and a priori one gets 2 copies of this EBMS algebra. A priori, right? But that's super confusing if you want to consider scattering, because that would tell you that the final data at Scri plus cannot be determined in terms of the initial data by the S matrix. They would differ by a supertranslation or a superrotation in general. So how can we actually make sense? Yeah. Yeah, because this M, the M is related to QS equal to 0, and that's related to, it is actually related to the phase space variables C and N via the constraint. Right. So you can write that in terms of C and N, and one can deduce the action of this quantity on the phase space upon using the constraint.
I see, but just to make sure, the only thing that I remember is some du of M is some related with the C and N.
We'll come back to that. Yeah, just hold on. We can ask later. Okay, so what it is did Andy show? So he showed that that a diagonal subgroup of actually just, so he only studied supertranslations at first. So BMS, sorry, the E stands for the superrotations, and just BMS would just be supertranslations. So he took BMS for the 2 copies, plus and minus, and imposed an antipodal identification of the supertranslations at Scri minus and at Scri plus. So this is obtained by an antipodal matching condition. I'm going to show it in a picture just in a moment. But this particular diagonal subgroup is a symmetry of scattering And in particular, he also showed that, well, actually, before saying that, maybe let's talk about what we mean by antipodal matching condition. Maybe that's more useful. So what do we mean by antipodal matching condition? So I'm just going to illustrate this in a picture because I don't have time to. It's kind of not that hard to explain. But yeah, so we have scry plus, and we have scry minus, and we have a sphere at the path boundary of scry plus. And we have another sphere at the future boundary of scry minus. Okay, and one can define this Q. We have some QS 0. We're considering just BMS, so I'm just going to consider QS 0 for now, plus here should be the same as QS minus, s equal to 0 minus, at omega A, where these two, the omega are just the coordinates on the respective spheres, and they're the two charges he demanded that they are equal up to applying an antipodal map that relates the sphere at scry plus to the one at scry minus. Sorry, what? No, so here we are literally just, this is not that shocking because you may expect, so in flat space, you should expect to impose boundary conditions at I0, right? So this is still allowed, yeah? So effectively what this means is that, first of all, this imposes the condition that there is no flux lost through no flux through I naught. And secondly, the reason for the antipodal matching is you can already see it, for example, in his lecture notes, that if you don't have any scattering, you can resolve I0 with a cylinder, and you can, it has to be the case that as a field propagates, as if you imagine a particle propagating from scry minus to scry plus without interactions, they will enter at the north pole here, and they will exit at the south pole in the other place, on the other sphere. So it's natural to impose this antipodal identification. Yes?
I have trouble figuring out why these are two squares. So scry plus the past should be the future of scry minus.
When you work in the coordinates I presented yesterday, you will see that these cover two patches of Minkowski space, and one has to glue them together, if you want, around I0. So they're not a priori related. The two sets of coordinates, they will miss that, they will break down at the future of scry minus and the past at scry plus. So one has to impose a matching condition there. Okay. From what I said so far, one can do the analysis independently in advanced and retarded coordinates. And you will find two sets of charges. And one can look in examples. So for example, in ENM, this is done in Andy's lecture notes. You can work out the electric field strength in Minkowski coordinates that cover the full space-time. And then you can take these limits where that field strength approaches the sphere at the past of scry plus and the sphere at the future of scry minus, and you find that the antipodal matching condition is actually built in. So so that's one way to see it. But yeah, there have been many sort of debates in the meantime, like is this, how physical is this? But certainly it's a choice that you can do, and you can study its implications. So this is what I'm going to do for the rest of this lecture. But before doing that, let me also point out that now this may seem kind of just so how can this be? So I explained the antipodal matching condition, but how can this be related to scattering? Well, we just said that there is actually a constraint that allows me to relate to extend this Q plus to an integral over scry plus. and similarly extend the q minus to an integral over scry minus. So so the matching condition plus constraint tells us that we have some quantities, some charges conserved in time, but Minkowski time, not retarded time now, right? Because we obtain some quantity now that is the same at scry plus and at scry minus. Yeah? So matching plus constraint tells us that there is a conservation under time evolution. The constraint is just, I'm going to do an example in a moment, but it's just this, I'm just going to write it down in a moment. But the punchline now is that since we have some quantities that are conserved under bulk time evolution, this means that the S matrix should commute with these quantities. Okay, so this means that we have some charges that commute with the S matrix. So in the notation that I introduced previously, we have Qs equal to 0s minus s, Qs equal to 0 minus, so these are function on the sphere here, in should be equal to 0. So at this point, maybe what I said is very hand-wavy, but you can assume this and see what are the implications if you don't believe anything I said. So it turns out that this conservation law is equivalent to the leading soft gravitance theorem. So I'm very lucky that Simon already discussed this in great detail in his lecture, so I don't have to tell you what it is, but basically, but now I'm going to show you how this happens. Sorry, so just in a picture, what is this leading soft gravitance theorem? I have a scattering amplitude, so we have P1, P2, and a collection of outgoing particles together with graviton that's soft, that is Q goes to 0. So this is related, this amplitude factorizes and is related to the amplitude via a factor, which Simon wrote down yesterday. So just to remind you, this is just, in this part, if you have n particle scattering, this would be sum from I1 to n of pi mu, pi nu, epsilon mu nu, depending on the helicity of the graviton, divided by pi dot q. And in particular, we have this pole. There is a pole as omega goes to 0. Now, how do we see this? Like, why is this true? And to see that, we can do the following. Now we're going to use this structure, this canonical structure introduced before to show this equivalence, or at least sketch how it's derived. So how to see this? So I think this is going to now address some of the questions that we got. So Q, remember that Q s equal to 0 is limit as u goes to minus infinity of this quantity curly m that was covariant yesterday, like constructed I haven't actually constructed it, but I stated what it was yesterday. So it's a function of retarded time and u. And I can apply Stokes' theorem at Scri plus, and I can write the following identity. So Q is equal to 0 at plus, at u equal to infinity, minus Q is equal to 0 at u minus infinity is equal to the integral from minus infinity to infinity of du of curly m. Okay, I hope this is no problem with this equation, hopefully. And now I'm going to assume that charge vanishes in the very far future. So effectively, we assume that there are no massive states.
And in that equation, do you mean m instead of q? Because in q, we've already taken the limit. Q is independent of.
Oh, I'm sorry. Yes, I mean, yes, thank you. I really mean this big Q. Sorry, for s equal to 0, there is no problem, there's no divergences. It's literally, yeah, it's the big Q that appeared yesterday. Q is equal to 0 is just curly m, indeed. It's just, I could have written m, but I want to relate. I want to write it in this charge language. Oh, sorry, this is, go to the other board. Okay, so how do we use this? The reason I've written this is that now I know, we know there is a constraint equation that determines the time evolution of m. Or equivalent, I could have written it for q, right? Remember, sorry, I erased it. This equation we wrote at the beginning, I'm gonna now use that. So we have that this is equal to a half d squared n of u plus, sorry, there is z and z bar everywhere, plus quarter c du n. You can check using the boundary conditions I've given that the recursion relation actually is this one. And now let's look at the let's analyze those two terms in turn. So I want to. So now, what effectively the problem amounts to trying to understand how to compute the insertion, the commutator basically, of this object with the S matrix, or equivalently, how to act with this on the asymptotic states. Either one would be good. So it turns out commuting this with the S matrix is complicated because we don't know what the S matrix is, but I can compute. I can use the Poisson brackets that I derived before to compute the action of these two terms on the asymptotic states. Yes? So this is what we're going to do now. So, yes?
Maybe slightly long question, but till we had not quantized anything, I was fine with the Poisson bracket. But because we've already gauge fixed things, usually the Poisson bracket, when you gauge fix, the constraints together become second class, and you have to change the bracket. So until we don't quantize, I think the algebra I'm fine with. But once you quantize, then you have to use some Dirac bracket construction, right?
No, but here I'm adopting the point of view where we have this, the Dirac prescription is to like find what are the physical modes, like the radiative modes if you want, and then commutators of everything else are computed via the constraints.
The thing that gets promoted to the commutator has to be this modified bracket and not just the Poisson bracket. Right? Like
Yeah, but we can talk, it's a subtle, we have, those things have been taken into account, but effectively here, well, let's discuss that later. So let's focus on this term. I'm going to call this Q 0 soft for reasons that will become clear in a moment. So the point is that this thing in the box is going to become a soft graviton, or it's going to be related to a soft graviton. So how do we see this? So Q soft is equal to 0. So we have C is the limit when r goes to infinity of 1 over r dx mu by dz dx nu by dz h mu nu, where h is the transverse traceless component of the metric, and this is up to some coefficient I'm not going to keep track of. I can mode expand it, and it turns out to be integral. Actually, there is a little calculation here because you have to take the r goes to infinity limit. So one has to like apply the stationary phase approximation. And, okay, so let me just say that there is actually some work. So you can see, for example, the lecture notes by Strominger. And one obtains just an integral over frequency if e to the minus I omega u a plus out omega x hat minus e to the I omega u a minus out dagger omega x hat. But I really need to compute the integral over u of n. But what is n? Well, n is just du of c star. And the integral from minus infinity to infinity of du of n is, I can write it as the limit as omega goes to 0 of a half integral of minus infinity to infinity du e to the plus I omega u plus e to the minus I omega u. So I'm just inserting this factor that is just 1, basically. Okay? In the limit as omega goes to 0, this becomes 2, and this is a half. So I'm inserting just 1 n of u. But this is just, so now we see that we get the limit of omega goes to 0 of just the Fourier transform. I mean, just linear combination of Fourier transform of the new tensor, and those are just going to pick out positive and negative frequency modes appearing here. And you have to take a u derivative, which is going to bring down a factor of omega. So at the end of the day, we're going to find limit as omega goes to 0 of omega, and then we have a out minus omega x hat plus a plus out dagger. Yeah? And now we see that this is just effectively, this is just a soft, it's a linear combination of soft modes. Yeah? And so the term in, so the boxed term d squared n is just dz squared of the left-hand side of the soft theorem. Yeah, so the left-hand side of the soft theorem is this, the amplitude with a soft insertion. Questions about this? So for the hard part, the calculation is a little bit more involved, but quite straightforward. And one can, so here, note that here I have not actually computed, I haven't used the brackets yet here. the Poisson brackets that I derived, or canonical commutation relations. But I just discovered that, okay, one of the terms in the conservation law, by the first term in the charge here, this Q soft term is just going to correspond to an insertion of a soft graviton. So all we have to show is that this quadratic term actually generates its action on asymptotic particle states is going to be, upon taking the Fourier transform, is going to coincide with the soft factor. And this can be done. So Q0 hard, did I call it? So this is the quadratic term. So I should call this Q0 hard. So one can take its Fourier transform and use the Poisson bracket between n and c derived before, promote it to a commutator to compute this thing, to compute the following bracket. And you're going to find that this is proportional to omega I and then delta squared z zi ai. Okay? So just intuitively, this Q hard is quadratic in the modes. You're going to find it's quadratic in the modes. So it's going to have an A and A dagger. And then A with A dagger is going to give you a delta function, and you're going to be left over with an A. This should be, I'm so sorry. This should be an actual, like another graviton mode, a finite energy graviton mode. It shouldn't have an index I. Omega I xi. And so now it doesn't quite look like, so what we obtain, so putting everything together, also using crossing, symmetry, so crossing of the soft graviton, one obtains some identity that tells you that dz squared, so limit as omega goes to 0 of dz squared of omega out a omega x hat s in. So z acts on this, sorry, I should say omega z. Is the sum over the other particle states, which I'm assuming here to just be hard gravitons, so that's all I'm assuming, is omega I delta squared zzi out s in. Okay, this is not exactly the soft graviton theorem, but how can I recast it into that? Well, I need to invert this operator, this dz squared. And I can do that by integrating against the Green's function associated to this dz squared. So the Green's function for dz squared is actually just z minus a w divided by z bar minus a w bar. We actually end up with exactly the soft graviton theorem. This turns out to be exactly related to the soft factor upon parametrizing the momenta, the massless momenta, as omega in a particular way that you can find. Any null momentum can be written as omega, the frequency times a null vector. And this null vector, you can parameterize it in terms of z and z bar variables as 1 x hat x hat of zi z bar I. So these steps can be filled in. I've left out a lot of the details, but I hope that the strategy in relating these two is clear. So I should pause to see if there's any questions. So everything is super clear or super confusing? Yeah, I know. Okay, so I'm going to assume that everything is very, very clear. So I'm going to move on to make some comments. So I'm not for the remaining 10 minutes. I'm just going to make some comments, and I'm going to leave you to think about them. So the first comment is that here I tried at least to very explicitly derive the equivalence between the leading soft graviton theorem and the conservation law associated to this QS equal to 0, which is related to the supertranslation charge. So the first thing you can ask is, what about QS equal to 1 and QS equal to 2? Yeah, because we have encountered these as well before. And this one, so any guesses what these could correspond to? Subleading, yeah. So subleading soft theorems. So this one is related to the subleading soft graviton theorem. So this was actually, for the first time, kind of surprisingly, you would think that maybe it's not very difficult to derive it, but it turns out that you cannot just compute Feynman diagrams to compute this. You have to use BCFW formula, and this was derived for the first time in 2014 by Cachazo and Strominger. So here it's at tree level. They only derived the tree level formula because BCFW, at least at the time, only worked for tree level. And shortly after, Byrne and collaborators, they showed that actually, so this subleading soft graviton theorem does receive corrections, but they are one loop exact. So these one loop exact corrections are not captured by this, but nevertheless, the tree level piece is actually universal, and it just can be obtained from a conservation law associated to superrotations in asymptotically flat spacetimes. And later, sorry, so this was derived from amplitudes first, and then it was obtained shortly after from conservation of QS equal to 1. So the superrotation charge. It's very similar, basically strategy identical to what I just showed. And at the same time, but in the same paper, what Freddie and Andy showed was that there is also sub-subleading soft graviton theorem at tree level that they couldn't really explain using symmetries. And in fact, this has been an open problem for a couple of years after. Campilli and Lada have some work on this in the where they argued that these subleading soft graviton theorem should be related to certain overleading diffeomorphisms. That, I mean, basically you have to relax boundary conditions that are imposed on the metric, and then they have some evidence that maybe this thing should arise as a conservation law associated to these charges associated to these overleading diffeos. But actually a more unified perspective was only found more recently, so in 2021, where with Laurent Friedel and Daniel Pranzetti were able to show that just from the equations, these master equations, from this Q du of QS is the qs minus 1 plus s plus 1 divided by 2 cn, sorry, c qs minus 2. So from these ones, we are able to write down this qs equal to 2 charge and compute and study basically apply the identical approach to what we did for the leading and had been done for the subleading soft theorems to derive this thing from conservation law of qs equal to 2. Okay, and now there was a question earlier. So far there seems to be a unified picture. You can understand the three-level leading, subleading, sub-subleading soft gravitance theorems that were proven in 2014 as conservation laws associated with these charges that can be extracted from Einstein's equations. But there is one funny other thing that one can deduce. So this other thing was actually first derived using celestial holography, but one can talk about it without talking about celestial holography, which is the following. So it turns out, but using only the methods that I described so far, it turns out, sorry, previously I told you what the algebra of qs equal to 0 and s equal to 1 was. I said it's related to extended BMS algebra. We now also have s equal to 2, so you can compute, you can put that in and see what is the algebra. And it turns out that s equal to 0, 1, and 2 obey the following algebra. So q, s, z. So z here means z and z bar. I'm just in the interest of time. So we can compute this Poisson bracket, and we can look at the linear component of this in n and c, and one finds that this is s plus 1, q s plus s prime minus 1, the linear part of that, dz prime delta z prime minus s prime plus 1, q s plus s prime minus 1, 1 of z prime, dz delta squared zz prime. It's just, yeah, you just find this, and for example, just to tell you what, so almost by construction, we know that, for example, if I take s prime is equal to 2, and I compute the bracket with s equal to 1, this bracket should just generate the Lie derivative with respect to Lorentz transformations on qs equal to 2. So that should be proportional to qs equal to 2. So in general, for s equal to 1, you see that you just generate, it turns out that you generate just this conformal primary, space-time primary condition on this field, roughly speaking. But a funny thing that you also notice is that if I set, so it's all good, but note that if I set s equal to s prime equal to 2, this bracket for that case, this right-hand side is only computed when I take, sorry, for s plus s prime is equal to less than 3, because I don't have, you see, if s is equal to s prime is equal to 2, in this algebra on the right-hand side, I would get a q3. But I don't have a q3 right now. I have not talked about that yet. So only, like, at first, you can, like, check for s plus s prime less than equal to 3. So on the right-hand side, you get at most s equal to 2 terms. But you may wonder, OK, what if I were, so this structure suggests that s with s prime for s equal to 2, we should get an extra generator for the algebra to close. So one needs qs equal to 3 for algebra to close. So how do we get this s equal to 3? So first of all, this suggests that there are further symmetries. So there should be some further symmetries. If you add in the s equal to 3 and you look at the structure, you quickly see that you need qs equal to 4 and so on and so forth all the way to s infinity in order to have a closed algebra. This algebra is known as, that bracket is known as the W1 plus infinity algebra. And we can actually get some qs equal s greater or equal to 3 charges by generalizing, by assuming this duq is dqs minus 1 plus s plus 1 divided by 2 c qs minus 2 holds for s greater or equal than 3. So if you assume these equations, there is some work that you can do, and you can extract in a similar way these higher spin charges. You can compute their brackets. You can explicitly check using the N and C Poisson bracket that we have the structure. What's remarkable is that you can also show that there is a connection between conservation laws associated to these higher spin charges and the tower of sub-subleading soft theorems. And finally, you may wonder, okay, but where do these equations come from? And I don't have time to explain that now, but we'll do this on Friday.
All right, so this is where I would direct everyone to go out for a photo, but our photographer is stuck in traffic, so we're going to do the photo tomorrow. We're changing the schedule, so we'll just have a regular coffee break now. We're back at 10:45.
Yes, yes.
Like,
Do you want me to unclip this?
Oh, sorry. Yes, please.